Welcome, engineers. Today, we're diving deep into a topic often overlooked but critical for any large-scale system: building a production-grade TCP log shipping client. It's more complex than it sounds, and mastering it separates good engineers from great ones. By the end of this lesson, you'll have a solid understanding of how to build a truly resilient system. First, you'll learn to implement a resilient TCP log shipping client, complete with automatic reconnection and exponential backoff, ensuring your data always finds its way. Second, we'll cover how to optimize network utilization and throughput through intelligent buffered batch transmission. No more wasting bandwidth with single message sends. Third, we'll integrate circuit breakers, a vital pattern to prevent cascading failures when your log receiver is unavailable, safeguarding your application's stability. Finally, you'll understand the essentials of a distributed tracing pipeline and how to set up a robust production monitoring stack using tools like Prometheus and Grafana. These skills are not just theoretical, they are directly applicable to the real-world challenges you'll face building scalable systems. Let's get started. Every large-scale system, from social networks to search engines, generates an immense volume of logs. We're talking trillions of events daily. But here's the often overlooked truth. The hardest part isn't generating these logs. It's reliably getting them from your application to your central logging system without losing data or crashing your application. Log shipping is deceptively complex. What happens when your application server crashes? You could lose valuable buffered logs. When network partitions occur, do you block your application or risk dropping data? If your log receiver is overloaded, does your client retry indefinitely, exhausting its own memory? These aren't theoretical questions. They are production incidents waiting to happen. The patterns we're building today, like resilient, buffered TCP clients with graceful degradation, are the foundation of systems like AWS CloudWatch Logs and Datadog's Agent. Understanding these trade-offs is what separates engineers who can simply make it work from those who can make it work at scale. Let's dive into the first two critical patterns for robust log shipping, starting with buffering. The core decision here is where to buffer logs before transmission. We have two main options: in-memory or disk-backed. In-memory buffering offers microsecond-level latency and is simple to implement. The trade-off is potential data loss on application crashes. For non-critical data like debug logs or metrics, where a tiny loss rate is statistically invisible, this is perfectly acceptable. Conversely, disk-backed buffering guarantees durability, but at the cost of higher latency due to disk I/O and more complex failure modes like a full disk. This is essential for critical audit logs or financial transactions, where zero data loss is paramount. Next, batch transmission. Sending logs one at a time is incredibly inefficient, creating significant TCP/IP overhead per log line. At scale, this wastes gigabytes of network bandwidth daily. Batching is non-negotiable. We typically use a time and size-based strategy, for example, flushing every 100 milliseconds or when a buffer reaches 100 messages. This balances latency. The worst-case delay is 100 milliseconds, with network efficiency. The flush interval is a tunable parameter, allowing you to prioritize fresher data or better throughput based on your specific use case. TCP connections are inherently unreliable. Networks partition, servers restart, and clients must handle these failures gracefully without human intervention. The anti-pattern here is aggressive reconnection, repeatedly hammering a server every few milliseconds when it's trying to recover. This can create a thundering herd problem, preventing the server from ever becoming healthy. The solution is exponential backoff with jitter. This strategy calculates delays that increase exponentially with each failed attempt, adding a random jitter to spread out reconnection attempts over time. This prevents thousands of clients from overwhelming a newly restarted server, allowing it to stabilize and recover. Now, let's talk about the circuit breaker pattern. When your log receiver is down, should your client endlessly queue millions of logs in memory? This leads to backpressure problems that often crash production systems. A circuit breaker, like the one found in Resilience4j, provides three states: closed for normal operation, open when the server is down and logs are immediately rejected to preserve application memory, and half open to periodically test if the server has recovered with limited traffic. A controversial but often necessary decision in high-scale systems is to drop logs when the circuit is open, prioritizing application stability over 100% log completeness. If absolute delivery is required, you need disk-backed buffering, which adds significant complexity. Finally, let's discuss observability. How do you debug a distributed log shipping system? You instrument the instrumentation itself. Our implementation exports key metrics, logs sent total to track throughput, buffer depth as an early warning for backpressure, connection failures total for network reliability, and circuit breaker state to know when logs are being dropped. The key metric to watch is buffer depth over time. If it's steadily growing, you have a throughput mismatch. Your application is generating logs faster than your network can ship them. This is a leading indicator for system issues, often appearing minutes before user-facing impact. This robust client handles common failure scenarios like server restarts, network partitions, and server overload, thanks to the patterns we've discussed. It's designed to prevent out-of-memory errors with bounded buffers. This pattern scales linearly. Need more throughput? Deploy more clients and Kafka partitions. Companies like Cloudflare and Meta have built their massive logging pipelines using these very principles. You now understand the core principles of building a production-grade TCP log shipping client. To test your understanding, consider for which types of logs might dropping data be an acceptable trade-off for increased application stability.